Hey, sorry for the delay. I have to restart my computer for some reason. I cannot start the Zoom minutes ago. So, okay, let's start today's material. So today we will talk about ensemble method. Okay, so we talk about the trees and talk about the case studies. So now we go to a next topic. This is the ensemble method, which is probably one of the two most successful machine learning algorithms or the ideas uh, in the predictive modeling. Okay? So one is you may all know it's the deep learning. One is the ensemble's idea. So these two are the two, I would say, the most successful ideas in the machine learning. So let's talk about the ensemble idea. So here we just touch some very probably the most uh, fundamental, just touch the ideas and use some simple ensemble methods as an example. It could be much more complicated. Okay, but that doesn't mean they are not doing well. They are actually very successful in terms of the prediction performance as well as the interpretations, which we will talk about later. Okay? So if you read any classic statistics textbooks, you will not find ensemble ideas. Okay? So most of them, they would just cover the model selections. So that means there was many models you can choose. And the goal is to choose one of them. Okay. Like for the multiple linear regressions. Suppose you have, let's say, 20 variables. You want to fit a multiple linear regression model using these 20 variables. So of course, there are many choices. So which model we should use, right? That's the main concern in the traditional statistics. Okay. And why is that? Because if we choose just one model, the good thing is the interpretation will be very easy because it's always easy to interpret just one model. And since we choose from a big pool, probably this will be the best one because we choose the best one, right? So it will also have a good predictive performance. So this is the goal. But now we are talking about the ensemble method. So that is not using one model, but using many models, could be multiple models. Sometimes we can combine like thousands of models together, right? So the idea is not choose a single model as our final model, but talking about how do we combine these models. Okay, so of course there are many ways to do the com combinations. So the easiest one is the equally averaged. And this is the one that we will talk about in this course. So we will talk about bagging and the random forest in particular. So both algorithms are equally averaging. Okay. And this works very well. Okay. But that's not the only one. And we can have some different ways to combine the models. Like for the boosting, okay, which we will not cover, but still a very popular machine learning algorithm. It may not be, it can be different weighted, like exponentially weighted model average. So this is a very specific boosting algorithm called AdaBoost. And there are some other ways to optimize the weights. And the weights are data adaptive. And that's called stacking. So there are many ways to combine the models, okay? And why is that? Because the goal is not really focused on the interpretation side, but really focused on the predictive model, predictive performance. We want to have a better performance in terms of the prediction, okay? And then you will have a natural question comes out is, so model selection, model combination, which one we should go with, right? Should we just select the models or combine the models? So the takeaway message is that, so that's actually is what missing in the teaching statistics or maybe some other science also. When we learn something, we always need to know that in what situation that method works well. And that part actually is very often that missing. Okay. So when we talk about model selection, and I believe most of the traditional statistics textbook, they never tell you why we need to do the model selection and in what situation we should do the model selection and in what situation we should not select the model. I think I read many textbooks, but I don't think I have any textbooks that mention that clearly. So model selection should be used when there is one model which is much better, significantly more accurate than the others. If we can find such single model which really beats the other models very in a substantial way, then of course we should go with model selection. Okay, and if that is not the case, if we cannot really find a single best model which is very obvious that it's much better than the others, then you should think about ensemble methods to combine the models. Okay, and so that's the purpose. And why people didn't use, why this ensemble modeling idea just came out recently, in like within 20 years. Why is that? Why not 100 years ago people have the ensemble? Actually, in over about 100 years ago, some statistician really had that idea. And the people had found that the oldest, the very first person that had this idea is about many years ago by John Tukey. If you're familiar with multiple comparison in the statistics, there is a Tukey's HSD confidence interval, and that is John Tukey. Okay, so he actually proposed a twicing method, just combine two models at that time. Why is that? That's a very first ensemble model idea because the computation power is very poor at that time. People do the computation by hands or by very low efficient machines. So we don't have that computing power to allow us to combine the models. Especially if you combine hundreds of models, it's physically not possible. So that's why the ensemble method becomes more and more popular these days because we have a very advanced computing powers that allow us to do that. Okay, so that's the main reason. Okay, so when we talk about the ensemble method, I have to talk about there's a very famous movie. It's a Japanese movie called Rashomon. Okay, Rashomon is a very old movie. Probably a few years ago, I saw there's the top 100 movies in the world, and this Rashomon movie is rated in the top 10, I think. So this is a very, very famous movie, but very old. So this is about four people from different perspectives. They witnessed an incident that one person was raped and the one person died, and they came to the court to testify before the judge, but they just told the story from different perspectives. But the interesting thing is that from their own perspective, the judge will had very different conclusions. Okay, so that's the Rashomon, that movie about. And in statistics, there is a term called the Rashomon effect. Okay, and what does that mean? So that means, think about if we have, let's say, a black box. Okay, the black box shows the underlying unknown mechanism that connects the X and the Y. X is the explanatory variable. Y is the response variable, dependent variable. Okay, so we have an unknown mechanism that connects the X and Y. So we have input as X and output as Y, right? And this black box shows the underlying mechanism. Very complicated, could be nonlinear, could be very complicated. We don't know, okay? And what is Rashomon effect? So we can fix models, right? To model the unknown mechanisms, okay? And sometimes it's very often that we can find there are multiple models. They all describe the relationship between X and Y very well. And you may ask, what do you mean very well? I can say they all achieve about the same prediction accuracy. Let's say the R square. They all have the very good R squares comparing with the others. Let's say we have 20 models. These 20 models, they have the R squares is about 90%. And they are the top tier models. And they may have some difference among these top tier 20 models. Maybe one is 91%, one is 91.5%, but they are very close. And they are the top level. Comparing with the rest of the model, they are much better. Okay, now this box is something which is the truth, right? Unknown. It's just like in this movie. Okay, we have an unknown. So nobody. So there is. So that's the fact. That what happens in that incident. Okay, and these models you can think about as a witness of this fact of this truth, but they just explained the fact or the truth from different perspectives. So one model explained the truth from that perspective. The other model explained the truth from the other perspective, right? And let's say we have 20 models. They have about the same performance, okay? But they are very different. So what should we do? Should we just use one of the models? Or should we just try to combine these models together to have a better picture of the truth, to have a more a unified or holistic view of the truth? Which one is better? Of course, the second, right? So combined models may be a better choice in this case. And then the next question is, okay, so you are talking about the Rashomon effect. That means there is more than one model that's about the same prediction. Is that common in statistics? And what is the driving force that makes this phenomenon stand out? So why this is common? And that is actually related to the model instabilities. Okay, and this phenomenon is especially common if we have a high dimensional data. So what is high dimensional? usually we have many, many predictors. Okay, so that go back to the very first lecture that we started talking about what is statistical learning. Remember, I showed you some examples. We have the span example. In span example, we have about 70 predictors. And then we go to the mass spectrum data to predict the prostate cancer. Remember, we have over 20,000 predictors. And then we go with the digital recognition data from the zip code. We have about 256 predictors. So for all these examples, we have much higher dimension than the traditional data that we see from the classic textbooks. In the traditional textbooks, if you see the examples that we have, usually have 3 variables, 2 variables, 5 variables. That's the number of predictors that we have. So that's low dimension. But in the high dimension, since we have so many predictors, and it's very intuitive for you that, of course, there can be so many models can achieve about the same performance, but they can be very different. One model choose these, let's say, 20 variables, and the other model which performs very close, but they can choose a different set of predictor because there are so many choice, so many options, right? So that is becomes more and more obvious. So that's another reason why we need to have the ensemble method, because the data collection techniques also improves very fast. Nowadays, the data set tends to be more and more complicated, right? To have higher and higher dimensions. Okay, so that's why the Rashomon effects becomes more and more common. Okay, so this is the simulation that is based on the Leo Berman's paper, that two cultures. So suppose we have just 30 variables in a regression problem. And so if we have these 30 variables and we want to choose the 5 variable models, so how many models can we choose from these 30 variables? So that's a very simple math problem. It's 30, choose what? Choose 5. So that's the answer, right? So that's just equals to what? So if you want to do the calculation, that's 30 times 29 up to what? Times 28 up to 26, right? And divide by what? Divide by 1 times 2 times 3 up to times 5. And that's the answer. If you do the calculation, you will have 140,000, about 140,000 5 variable models that you can have. So among these so many models, a big pool, he found that we have many models, they can achieve about the same performance. So here, Leo Berman focused on the residual sum of squares within 1% of the best models. So let's say the best model has the smallest RSS, residual sum of squares. And he found there were many 5 variable models. They have the RSS within 1% of the best. Okay, these are the just 3 models that he showed you as an example. And you can see these 3 models are very different. Model 1, he called it not model 1, a picture 1. Okay, model 1 used X3, X8, X12, 13, or 17 like that. And the model 2 is this, and the model 3 is that. So they are very different. You see that? So these are the 3 pictures that taken from different angles of the truth. So that's why he called it pictures. So if we want to know the truth, it's better not to use just one picture. It's better to what? It's better to use all of them. So that's the example that he showed in his paper. Okay, and this is not, Rashomon effect is not just in linear regression. It can be in many different models, like the trees that we will see in a minute. And also, like in artificial neural network, I will show you one example for the Rashomon effect in the artificial neural network when we reach the ANM. Okay, so this happens in many different types of models. Okay, and this is closely related to the model instability. Okay, so this is the main motivation that people go with the ensemble idea. Okay, so this is just a simulation, very simple simulation. The truth is that function, that sine function in the background. You can see the sine function, right? That's the true function. But of course, when I generate the data, these are the open circles in the, so these are the sine function plus some additive noise. And based on these observed data points, and then I fit a regression tree. So you can see the blue step function is the fitted regression tree to approximate the underlying, the smooth, the sine function. Okay? Then I use a technique, a resampling technique called bootstrapping. Okay? So I use the bootstrapping to generate 100 trees. Okay, so what is bootstrapping? So the bootstrapping is sample with replacement. Okay, sample with replacement. So that means, let's say we have 5 samples. Okay, we have say 1, 2, 3, 4, 5. 5 observations in the data set. So what is a possible bootstrap sample? So bootstrap sample should have the same number, okay? Usually have the same number. So a bootstrap sample is, we can sample with replacement. So let's say 1, 1, 3, 3, and 4. So that could be a possible bootstrap sample. So the first one that I randomly pick one, maybe 1. Okay, and the second one that I randomly picked from 1, 2, 3, 4, 5, again, we get another 1. Then the third one, we picked 3, 3, and 4. So this could be a possible bootstrap sample. It's sample with replacement. Then this is a new data set. And I call this is a bootstrapping data set. Bootstrap sample. Does that make sense? Now this bootstrap sample contains 2 first observation, 2 third observation, and 1 fourth observation. And then I can fit a tree using this bootstrap sample, not from this original. Is that clear? So this is a bootstrap sample. Of course, here I'm just using a very small example, just 5 data points. So here we have more than 5, okay? And anyway, using the bootstrapping idea, so bootstrapping you can see is a resampling technique, okay? And each bootstrap sample, I fit a tree, I fit a regression tree. So you can see in the background, we have those red curves, and these are 100 trees, regression trees, fitted based on the bootstrap sample. So I randomly sample 100 times. Each time we have a bootstrap sample, right? And for each bootstrap sample, I fit a regression tree. And I have 100 that regression trees. So these are the 100 trees. You can see the red curve. And then you can see in the background, you can also see a blue curve, which is different from that. And you can see the interesting thing is that now the blue curve is not that sharp at the corners. It's kind of like using the sandpaper to sand off the corners to make it more smooth, right? You can see in the background is. So this is what? This is the average of these 100 trees. Of course, this is a very simple example, okay? But the example just give you some idea that the trees are not stable, right? If we change the data slightly through bootstrapping, and you can see we can have different trees. And then maybe it's a good idea to average these trees. Okay, let's see the performance. So this is the RMSE. What is that? That's the root mean squared error. Okay, so root mean squared error. So what is the mean squared error? Let's say we have yi, that's observed, right? And the yi hat, and that's what we predicted from the model. So we take the square, is that right? And of course, we need to take the summation, right? We have, let's say we have 100 data points, I from 1 to 100, right? So that's the sum of squares error, sum of the squared error, is that right? So what is the mean squared error? MSE. MSE is you have to divide by what? We have 100 observation. This data set, let's say we have 100 data points. So we need to divide by 100. So that's the mean squared error. So that's the MSE, right? And what is root mean squared error? Root means square root. So square root means we take a square root of that. So that is the MSE. Okay, so that's by definition is the root mean squared error. That's the RMSE. Is that clear? And why we need to use RMSE? The good thing for the RMSE compared to the MSE is that RMSE is in the same unit as Y. Let's say Y is dollar. Okay, let's say here the dependent variable is the income, is in the dollar. And what is the unit for the RMSE? It's also in dollar. But what's the unit for the MSE? It's dollar square. So when we have the RMSE, it's much easier for us to interpret the results because it has the same unit as the dependent variable Y. So that's the main reason. Okay, so you can see for the using a single tree, the RMSE we got is 0.15. But if we use 100 trees from the bootstrap sample and then take the average, you can see what is RMSE. It's decreasing to 0.13. Okay, if you do some calculation, you will see this improved by more than 1%, more than 10%. If you do some calculation, relatively speaking, this is better than this by over 10%. Okay, so this over maybe close to 20%. It's bigger than 15%. You can easily do some calculation and you will see that. But anyway, this just gives you a very simple example that when we combine the models, just by very simple combination, the simplest way to combine the model is just average, right? Nothing tricky, just average. And you can see even by that, we can substantially improve the performance. Okay, so this is just give you very simple example as an illustration. Okay, now this is the classification example. Very similar to this one, but the only difference is this is in the classification case. So suppose we have very simple class boundary. It's just in diagonal lines. Above the diagonal lines, red, below the diagonal lines, blue. Okay, and we have some observed data points. And I use the classification tree, not the regression tree, to do the to classify. And this is the single tree that based on the whole training data. You can see it approximates the linear boundary by the step functions, right? And then same idea, do the bootstrapping, and then 100 times I have 100 bootstrap sample, and then each bootstrap sample we fit a tree. Okay, so then we can, so in the background you can see the gray lines. These are the fitted 100 classification trees. Okay, and I can combine the 100 trees in two ways. Okay, so one way is to do the average. And you may ask, how can we do the average for the regression tree? Oh, for the classification tree. Don't forget that for the classification tree, you can have two types of output. When you do the prediction on the classification tree, you can have two options at least. One option is to predict as a class, right? Then it will tell you it's red or blue, yes or no, right? Success or fail. So that's one way. Another way is what? Another way is instead of giving you which class, it gives you the probability that belongs to the red class and the probability that goes to the blue class. Is that right? So here, the average tree is what? For these 100 trees, we take the average for the probability of the red tree, let's say. Of the red, not red tree, red class. Okay, so if the average the probability for that particular sample of being red class is more than 0.5, then we just predict this is as a red class. If the probability of being red based on the average of these 100 trees is below 0.5, then we just predict as blue. Does that make sense? So it's just simple average on the probability level. Okay? And there's another way to combine these 100 trees. And that's actually through the voting. Because each tree can give a vote, right? So here we can do the vote. So for each data point, we can have 100 votes, one for each tree. Is that right? So we use the majority vote as our final prediction. Okay, so there are two ways to combine these 100 trees. And you can see these two ways are very similar. So you can see the red curve and the blue curve are very close together, almost perfectly matched. And for the misclassification rate, you can see if we just use a single tree, the miss rate will be 6%. But for the combined, it's very close. It will be 3.4 for the voting and 3.5 for the average. Is that clear? So this just gives you two examples for combining the models in the classification and in the regression. Okay? Okay, so bootstrap, this is just one slide that explains what is bootstrapping, okay? And the original purpose for the statistician that developed bootstrapping is what? Is not in combining the models. Is actually to use to estimate the uncertainty of a statistic. Like we know that if we are talking about the average, the mean, the standard error is very easy to check, right? If in a data set we have the sample standard deviation is S, that's the sample standard deviation, S. What is the standard error for the mean? The standard error for the mean is what? Is S divided by square root of N. That's very easy to get because we have a closed form formula. Is that right? But what about now? Now let's talk about not the mean. What if I'm talking about the median? Okay, so I have a data set that's what is the standard error for the median? I don't know. There is no closed form formula for that. And what about the quantiles? Is there a formula for the standard deviation of a quantile? No. So just in short words, there are many statistics that we don't know the closed formula for finding their standard error. Okay, so in reality, if we want to know what is the standard error for that statistic, what should we do? Bootstrapping is the main approach. We can use bootstrapping to estimate the standard error or to find out the confidence limit for a statistic. Okay, so that's the original purpose. But now we're using the bootstrapping as a resampling technique in the model combinations. Okay, so this is just some simple story about the bootstrapping. Okay, now the reason I add this line is that I want to have a connection with the B-spline smoother that we talked about before. Okay, so remember we talked about the smoothing splines, the B-splines, the natural splines, right? So we can also use the bootstrapping to find out the confidence intervals. Okay, so because usually it's not easy to find out the standard error for a fitted B-spline smoother. Like here we have a data set. We can fit the B-spline smoother, right? So what is the standard error band, right? We can use some formula to approximate the standard error bands, but that may not be data adaptive, especially if we have some outliers. So you can see in this data set, we have some outliers. These points that are circled are outliers. Why I say these are outliers? Because they are far from the data estimated curve, far from the majority data points. Is that right? So these three that I circled, and also maybe this one, these are outliers. So if we have outliers and lots of outliers, the parametric formula, even if we have a formula for the standard errors, and we call it that's the parametric form, they may not doing well. Okay? So what we can do is we can use bootstrapping to create a data adaptive bootstrap confidence interval. So you can see the bootstrap confidence interval is in the, so this shows the bootstrap curve, and this shows the confidence band based on the bootstrapping. And this is the confidence band based on some formulas. This is the parametric approach, and this is based on the bootstrap. So you can see for the bootstrap approach, this is more data adaptive. Why? Because if you look at these outliers, right? The one that I drew the lines. So these are where we have the outliers. Like we have the outlier here, we have outlier here, and also we have some outlier here. Look at this place that we have outliers. The upper limit is much larger than the lower limit. You can see these standard error band are dragged by those outliers. But for this one, it's almost symmetric, right? It's symmetric. So it's not really data adaptive. So you can see that's the benefit of using bootstrapping. It's more data adaptive. Okay. Of course, this is a little bit beyond the topic for this course. So I'm just giving you one example to show the usefulness of using bootstrapping in the statistical inference, model inference, okay? Which is not the main topic for this course, but I'm just slightly cover this. If you are interested in that, you should read the elements of statistical learning. Okay, that's one of the reference books, elements of statistical learning. And that's in this book. Okay, now any questions so far? Okay, now let's talk about the bagging. Okay, so bagging is developed by Leo Berman in 1996. The bagging name means called bootstrap aggregating. Okay, so bagging, the idea of bagging is very simple. Okay, is just to use the bootstrapping to get the bootstrap sample. And for each sample, we fit a regression tree or a regression model. That it doesn't have to be a regression tree. It can be a regression model or classification model. Then we combine. Okay. In other words, these examples that we see here, these are the baggings. This is bagging for the regression case. This is the bagging for the classification case. But here, the bagging, I'm using the tree as the base model. Okay, so it doesn't have to be tree. We can use, like, for this one, we can use smoothing splines and do the bagging on the smoothing spline. That's fine. And we can use like some other like the logistic regressions instead of trees, and then do the average. That's also fine. So bagging is not just for tree, okay? But tree can be a good choice, and we can use some other. But the idea is that we need to use the bootstrap samples to fit the models repeatedly. And then we just combine these models. And how do we combine? For the regression, we can just do the averaging. For the classification, we can do the voting or the averaging in terms of the probabilities. Okay, so that's the bagging. Okay, so when does it work? So when the bagging works? The bagging works when we have unstable models with similar performance. And that's very important condition. In other words, if the model that you use is a very stable model, you should not use it as a base model for the bagging. The bagging actually likes those models which is not stable. Because if the model is very stable, all these bootstrap sample gives you the same model, then what's the benefit of combining these models? Because if they are all the same, you combine them together, you will be the same model, right? So the benefit of using bagging really comes from you are adding together different models. So that's the why. So that's why the stable model is no good. And you may ask, what are the stable models? Here I'm listing some like linear regressions, logistic regression, and you may say these are not they can have Rashomon effects. Yes, but this stable and not stable, it's a relative term. It compared with nonlinear model. Linear model is more stable, right? Compare with nonlinear classification methods. Logistic regression is more stable. Does that make sense? It's a relative term, okay? And for the tree, I listed it as a stable, but don't forget the first word, the word before the tree. It's a pruned tree. If the tree is pruned, then it's stable. If it's not pruned, so it's unstable. So that actually gives you idea that if we do the bagging tree, should we just do 2 steps or just 1 step? 1 step. We can just construct a tree without pruning in the second step. Okay? So model, and also when the model in the bagging works, the model should be a nonlinear or adaptive function of data. That can benefit the most. Why? Because you can see here, this, like here, these are nonlinear models. If we combine them together, it will be much more complicated, okay, than a single nonlinear curve. And then just like tree, if we combine them together, you can see the average of trees can be very different from any single trees because it can become kind of smooth. Is that clear? So you can see the benefit is really happens if we have a nonlinear or adaptive function. So that's why bagging usually not applied on the linear model. Why? Because for a linear model, if you combine many linear models, the model is still a linear model. You see that? So it doesn't really extend the model space by combining linear models, because the combined linear model is still within that linear model space. But if you combine many trees, the final tree is outside, is in a much bigger model space than a tree space. So that's the benefit, okay? And third one, the parametric bootstrapping. So this one we can just skip. So this is a connection between the parametric bootstrapping to the original fit. But I don't want to get into the details about what is parametric bootstrapping. So let's just skip that one. How does this work? Why bagging can improve the prediction performance? And that actually go back to the fundamental principle in the machine learning and statistical modeling is the bias variance trade-off. Remember, we have a bias variance trade-off. We talk about that. The mean squared error to predict a new data points depends on three components. The first is the bias square. The bias square. The second is the variance of the model. And the third one is the irreducible error. Then this one cannot be changed. So this is the sigma square. That's the building the data. So we cannot change anything on that. It's there. And what we can choose is this and this, right? So bagging is really not touching that, is not reducing the bias. But bagging can reduce the variance through the averaging. So the main reason why bagging works can reduce the prediction error is because of the variance reduction through the average. No effects on the bias. Okay, so that is the underlying reason why the bagging works. So now this statement leads to, this statement leads to the next slide. It just shows you a very simple proof. Very simple, okay? Suppose we have a set of estimates. So these are the each models from the, based on each model is fitted from a bootstrap sample. So we have model one, that's called F1 hat, model two, F2 hat, to the model K, FK hat. Okay, so let's say we just take the simple average, right? That's what we do in the baggings. We just use the simple average as our final estimate. So our final estimate is called F hat B. That's the bagging estimate, which is the average of all these models, right? Okay, now let's check the variance. Okay, so the variance for the bagging estimate is this one. Okay, I don't want to go to the details. Okay, but here, let's say assuming these models, they have the same covariance. Okay, and then each model, they have the same variance. Okay, then we can get the variance for the bagging estimate is equals to this one. Okay, a rho is the correlation between any two models. Okay, rho is the correlation. So what is the range of the rho? Rho is between 1 and the -1. So any correlation is between -1 and 1, right? And in here, for all these models, obviously the rho should be within 0 and 1 because they should be positively correlated, but no more than 1, right? So it should be in this range. So now let's see, this is the variance for the bagging estimate. So the second term actually goes to 0. Okay, you may ask, what is the B? Here, my notation is very sloppy here. B should be the K. So here, B should be the number of models. So B should be the K, okay? So it should be the K. So when the K goes larger and larger, if we bootstrap that many, many times, so the K can go to like 1,000, right? We can do the bootstrapping 1,000 times. So if that is case, so if the B, which is the K here, goes larger and larger, the second term I claim goes to 0. Does that make sense? Because 1 minus rho is just a small number, right? And sigma square is a constant, so it will goes to 0 if B large enough. But so it really matters is this term. So this is rho sigma square, obviously is what? No greater than sigma square. And what is sigma square? Sigma square is the variance for each single model. So the variance for each single model is sigma square. So you can see the bagging really reduce the variance because the variance of a bagging estimate is rho sigma square instead of sigma square. Is that clear? So that reduces the variance because the rho is between 0 and 1. Okay, so that's the simple proof. Okay. Okay, so now let's see an example. So this is the bagging with trees. So we generated a sample of 30 observations with 2 class and 5 features. And each feature is generated from the standard normals. And we have the pairwise correlation is that. Then the response is actually this one. The probability for the y being 1 is when the x1 is less than 0.5. Otherwise, if it's greater than, then it's 0.8. Okay, so this is 0.2, this is 0.8. So basically, we have 5 variables, but the underlying truth is that it only depends on the first variable. Okay, so if we know the truth, what is the best model? The best model, of course, is using the x1 at the 0.5 or not. Right? If it's greater than 0.5, we should predict as what? Y equals to 1. Because the chance for y equals to 1 for x1 greater than 5 is large. But when the x1 is less than or equal to 0.5, it should be what? We should predict as y equals to 0. That's another class, right? Because the chance of y equals to 1 is 0.2. That means when the chance of 0 or y equals to 0 is 0.8. Okay, so that's the underlying true model, right? So even the true model, we have an error. The Bayes error is 0.2. Why? Because it's a probabilistic model. Even though we know the truth, but the chance of y equals to 1 given x1 is greater than 0. Is not perfect. It's not 1, it's 0.8. So we still have 20% of chance having mistakes. And same thing for here. So the Bayes error is 0.2. Okay? So a classification tree was fitted on the training data with 200 bootstrap samples. Okay, so this is the setting. And you can see here, this is the original tree. Original tree means what? This is the tree fitted by the original training data. We have 30 observations, 5x, right? So this is original. So you can see the first split, we use the correct variable x1. But the tree didn't stop here. It just have this. And the rest of the 5 models, B1, B2 to B5, these are based on the bootstrap samples. So B1 is using the first bootstrap sample. We fitted a classification tree, and that's this one. So and B2 is the second, and so on. So you can see for bootstrapping trees, the variable, they can be very different, right? We can use different variable to do the splitting. And you may ask why they use different. Because if you look at the data generating method, the X are highly correlated. The pairwise correlation between any two X, X1 through X5, the pairwise correlation is 0.95. Okay, so that's why X2, although it's not the underlying true variable should be used, but it still have very strong similarity as X1. So that's why some of the trees using bootstrap sample not picking X1, but picking X2 or 3 or 4 or 5, because they have very high pairwise correlations. Okay? So when we combine it, let's now, so this shows you the tree. So you can see the tree structure are very different, right? And when we combine these trees as the bagging trees, and this shows the test error, okay? And this shows the number of trees that we added. And you can see the original tree, just use one single tree, the test error is about close to 0.45. But for the bagging trees, and we have two ways. The consensus is through the majority vote, and the probability is through the average of the probabilities. Okay, so you can see the prediction accuracy on the bagging trees. They are very similar. This approach are very close to here, 0.36 maybe. So which is a big improvement. You see that? There's a big improvement that if we combine the trees. Okay, so this just show you a simulations example. Okay, so why bagging tree and bagging in general? So why we use trees? Because the trees usually can capture the complex interaction structures, and tree can handle mixed type of data and missing values, and with large depths, the tree can have relatively low bias but high variance, right? And if the underlying fx, if the underlying function is smooth, and bagging tends to reduce the bias by sending off those corners of the step functions. So that's the reason why bagging is commonly coupled with trees. Okay, that's why tree is used very often as a base model for the bagging algorithm. But the bagging is not limited to the trees and bootstrap samples. There is a paper in 2006. It shows the bagging can be used not using bootstrapping, using some other resampling method, and also not for tree. It can be using some other models. Okay, so but sometimes the bagging does not work, but that is not often. Okay, so when the bagging may not be working, bagging is unstable with respect to the training set when we have some extreme outliers. So that could be one of the possible reasons why bagging doesn't work. And another is to bag a stable model may even make it worse because there's no benefit of combined stable model. And sometimes bagging can make it worse if a simple model is better. Remember, we talked about when we should ensemble, when we should select models, right? Let's say if the f underlying function is a step function, then just use a single tree, right? Why using combined trees? Just using a single tree is good enough. So that could be another reason, okay? But all these are not common in practice. So we talk about the bagging through the simulations. So this is the applying the baggings to the real data sets. And that is also in the original paper for the bagging predictor by Leo Berman. And you can see here for the classification, he applies to many data sets. Okay, so these shows the data set's name, number of observations in the training data, and number of variables in the data set, number of classes. So these are the classification problem. And this is the misclassification error for a single tree. This is the misclassification error for a bagging tree. This is the improvement or the decreased in percentage for the by using the baggings. Relative improvement. So you can see by using the baggings, the improvement can be up to 43% in these examples. And even the worst case, it can be improved by 6%. Okay? And these are the regression examples. Right? And these examples are relatively small data sets. So he also chose some large data sets. Okay? And you can see for the large data sets, the improvement can be, some of them can be can improve by 77%. So this also shows a good example when we propose a method. So Leo Berman is not just showing by one or two examples. He actually applied bagging idea to many, many examples. And the bagging shows the consistent improvement on many, many real data sets. And this is also validated by so many researchers later on. And I use bagging also many times, and bagging usually performs much better than a single model. Okay, so that's the bagging. Any questions? And next time we will talk about the random forest. So, but here I would like to stop here. Next time not the random forest. Next time I will talk about some case study for the baggings. Any questions before we dismiss? Okay, if you don't have any question, let's stop here. Bye-bye.